Uh, Good afternoon, everyone. I want to welcome you to my lecture today. I also want to welcome you to the new month, March, and the new topic. Of course, we're in chapter 7 of the textbook. So the focus today will be on the variance stabilizing transformations and weighted least squares. Okay. In that line, I'm going to walk us through unequal variance, data method, then the weighted least squared. Okay, give me 1 second. Now, why are we doing what we want to do now? Because if there's a practical problem and we want to seek redress from statistical framework, maybe we are interested in figuring out the relationship between variables. And we want to use linear regression model. I told you the other time. We got assumptions. Every statistical model has assumptions. Let me first confirm, those of you online, I need you to confirm if you're hearing me clearly. Is everyone hearing me clearly? Those of you online?
Yep.
Thank you so much for confirming that. Okay, so we got different, assumptions using the linear regression, assumptions of linearity, normality, constant variance, and so on like that. What's of in a situation where the assumptions of constant variance is violated? What do we mean by assumptions of constant variance? We're trying to say the variance of the response is basically going to remain the same given any value of predictor. That was what we said, right? You know what that means? It means if I'm looking at the relationship between X and Y, okay, if I'm looking at the relationship between X and Y, okay, all the observations should have the same weight. They should have equal weight. That's what we mean. But what if in a situation where some observations have, they have more information than some observations? I'm going to say that again. What if in a situation where some observations, give more information than some observations in your data set? In that situation, you can never have equal variance anymore. It means some observations are more informative and some observations are less informative. Those ones who are more informative, they will have huge weight. They're basically going to have more weight. Okay, more weight. So more weight for those who are more informative. Okay, more weight for those who are more informative. Okay, but less weight for observations that are less informative. Let me confirm this. Those of you online, I really want to see. Can you see the board, right? Those of you online, can you see the board? Can you confirm if you can see the board? Those of you online.
Yeah.
Oh,
We can.
thank you so much for confirming that. Because at times I normally write something because at times you may not understand my accent. So that's why I write. Okay, thank you for confirming that. Okay, if you take a look at this picture now, where you are looking at the relationship between that response and the predator. Now, my question now, can you call this a constant variance? Okay. So from what we are saying, we may not be able to call this. But let me tell you this. We got a way to investigate, to test for that assumption. Okay. Situation where we test or we look at the graphical way, and there's a violation of that assumption, the ordinary least square method, the method that we've been using before, is no longer appropriate. We need an extension. We need a generalization of that method. The generalization of that method is basically going to be called a weighted least square. Weighted in the sense that some observations in my data set, they are more informative than others. And you know what the conventional linear regression suggests, I mean required, and is they assume that all observations are equally weighted, which means they all give the same information. That's what they mean. Okay. Now, why is unequal variance a problem? Just like I told you the other time, if I basically want to investigate whether my model is valid, I need to investigate assumptions, whether assumptions are met or not. What if in a situation where we investigate assumptions of constant variance and is violated? If I ignore that and I make a recommendation, then I'm actually going to mislead. But what is going to be the consequences? Number one, the consequences that we're basically going to see is that even though the estimate of your beta, the estimate of your regression parameter will still be unbiased as required, but the variance will no longer be minimal. You know that when we obtain our beta cap, we also want to obtain the variance of that. We also want to obtain the standard error. Why do we need a standard error? Without standard error, I can't conduct inference. What do I mean by inference? Constructing confidence interval or testing hypothesis. I need a standard error. But let me tell you this. In a situation where there's a violation of our assumption of constant variance, this is still going to hold. This is unbiased. It's still going to hold. But this guy will no longer be a minimal variance. And when the variance, that means the variance will be tampered with. When the variance is tampered with, then so the standard error will be tampered with, because the standard error is the square root of variance. And that was what I said here. Okay. Now, intuitively, observation where variance is smaller should count more. Do you know the observation where variance is smaller? Those ones that are more informative. Those ones that are more informative, they're basically going to have a huge weight, less variance. Those ones that are less informative in the observation, they're basically going to have a smaller weight and huge variance, because the relationship between variance and weight is inversely proportional. The more the variance, okay, the less the weight. The lower the variance, the more the weight. Does that make sense to everyone now? Okay, that's exactly what we mean. And let me also tell you this. If the variance depends on X, because what we're trying to say, initially, what was the assumption? The assumption is that variance of Y does not depend on X. That's a constant variance, right? But in a situation where observations They don't give the same information. Some are more informative than others. Then there's going to be a violation of this guy. And when there's a violation, and that was why I said, if the variance depends on X, then your prediction interval should be wider. Oh my God. Do you know that if I really want to know whether to trust my estimate, you know what I normally do? I construct a confidence interval. I construct an interval. If the interval is wider, that's more errors. You don't know that? Wider means you have a more standard error. You have a more margin of error. That is the reason. And that's exactly what we're trying to, to talk about. Okay, and I said, of course, even though there's some robustness, even though we have a violation, there's some robustness. Okay, but I said tests have approximately the right type 1 error probability when the number of observations at each combination of X value is large and roughly equal. Let me tell you this. Statistical tests have some form of robustness, but the robustness, at times, that depends on the level of violations. In a situation where we got different weight, where observation got different weights, then the variance will actually be tampered with. Then we now need an intervention that will stabilize the variance. And that is the reason why I actually call the title variance stabilizing transformation, because we know when some observations give more information and some give less information, then we're actually going to use a regression technique that will treat observation in an equal manner. And that's exactly what we want to do. Statistics is like a story. Okay, now we have already established, we've acknowledged the fact that there's a problem, right? Then how do we fix it? We got two ways to fix it. Well, what am I talking about? Two ways to fix what? Two ways to fix situation where assumptions of constant variance does not hold anymore. Number one, we use a variance stabilizing transformation. If you take a look at the title, there are two things in the title. What you see in the title, they are the two possible solutions to fix the problem. Number one, we can do a variance stabilizing transformation, or we use a brand new model, which we call the weighted least square. Does that make sense? Okay, so when you take a look at the two ways to fix the problem, the number one way to fix the problem is to go by a way of variance stabilizing transformation. So, and I say the variance depends on the expected value of y. In a situation where variance depends on mean. In statistics, variance and mean should be independent. But in a situation where variance now depends on mean, the variance of what? When the variance of the observation depends on the mean, you know what we're going to do? Then we need to transform the response variable. Oh my God. Is that the reason why at times we may see a log on the response or square root on the response? So, which means the idea of transforming the response actually comes, when we realize that the variance of the observation actually depends on mean. Now, what is the other approach? The other approach is to use a weighted least squared. And we use that if the variance is proportional to some constant. When I say variance proportional to some constant, variance depend on weights. Observation with more information, we have a smaller variance. And we have more weights. Does that make sense? Observation with less information about what? More or less information about the relationship between the variables. That's what we mean. Any question? Okay, you made the example of where some observation could have more or less information. There's so many of that. I think I'm going to give you example. You know, when I mean observations, I'm talking about it could be persons. For instance, maybe I want to look at the relationship between blood pressure and maybe or let me just say relationship between advertising, amount I spend advertising, and the volume of sales. Of course, I'm actually going to use observations. Maybe I collect it over 50, maybe I collect 50 observations, which means I'm going to have 1 to 50 over the two variables. You know, when we look at the 50 assumption is that the variance of the observation given any value of x should be the same, should be sigma squared. But at times, we may look at the data set and realize that some observations are more informative and some are less informative. But of course, to be able to, we have a way to detect that because we have a way to, we're going to test for constant variance. Of course, we have some tests that we can use, which I'm going to walk you through. We call Brecht-Pegan tests and so on like that. I think I'm still going to give you the real life example. That's a very good question. Now, do you know that apart from those two that we talk about, we have a method that we call data method. You know what data method? Data method is an example of a variance stabilizing. But the data method stabilize variance in a special way. You remember when I walk you through this example in one of my lecture, right? Where we want to determine the optimal values of temperature and the baking time, right? On a cake, right? Okay. You know, of course, maybe looking at the observations, some are more informative and some are less informative. Of course, because of that, we cannot trust the standard error that come out here. What do we do the other time? We go by way of optimization. If you remember in one of my lecture, if you can go to the slide, we went to optimization, we differentiated the main function with respect to x1, with respect to x2, and we derive a new standard error. The new standard error here are the stabilized, the one we got through stabilizing the variance. So this approach is a way of stabilizing the variance because of the fact that we cannot trust the other one. Okay, that's what we mean by that. Now, let me now come to the weighted least square now. What was the assumption in the standard linear model? The variance of the error must be sigma square, right? Not only variance of the error, of course, you know, variance of y given x has to be sigma squared. Okay, so which means we expect the variance of the error to be sigma squared, to be constant, right? But what if in a situation where there is a weight? And that's why I said there are instances where we don't have sigma squared, where we're actually going to have sigma squared divided by wi. Why do we have a wi? The wi here is like, you know, I'm having like sigma squared 1 over wi. Why is it reciprocal? Because relationship between variance and the weight is inverse. The more weight an observation has, the less variance. Does that make sense? And the less weight, the less weight. If observation has less, you know, more contribution or more information means more weight. Less information means less weight. But if you want to look at the weight and the variance, they are inversely related. So what we normally see in a situation where we don't have equal weight anymore, the variance of y given x equal to that equal to the variance of error will no longer be sigma squared, but sigma square over W high, where W high is basically going to be weight. So what are you trying to talk about? It means every observations have their weight, and they are not equally weighted. Some have more weight than the others. Who are those that have more weight? Those who are more informative. Those who are more informative have more weight and less variance. Those who are less informative has less weight but more variance. Does that make sense? That's exactly what we mean here. Now, and I said the weighted least squared is an extension, it's an estimation technique which weights the observations proportional to the reciprocal of the error variance for that observation, and so overcome the issue of non-constant variance. So the only way to overcome the issue of non-constant variance is to basically to consider a new form of the variance of the error that will be weighted. Does that make sense? Let me tell you something in statistical analysis. If I have a reality and a model, before my model can actually adequately represent reality, they must have an agreement. How can I use a model that assumes equal weight with data set that assume no equal weight? But when I use a model that assume no equal weight with relationship that assume no equal weight, what happens? They go together. That is what we always want to do in statistical analysis. There must be an agreement between the nature of your model and the reality. If there's no agreement, there's a violations. Does that make sense? And that's exactly what we're doing now. We know that there's an unequal weight in our data, and that's why we're using the variance that is also weighted. Weighted variance of the error on the weighted relationship. That's what we mean. Okay, we want to go back into the linear regression model now. But in this linear regression model specified, there is a violation of assumption of constant variance. Do you see the error, right? Error follow what? Normal distribution with a mean zero. But what is it? What is the variance? Sigma square over W, where the WI is the weight, which means if you collect 50 observations, how many weights are you going to have? 50 weights. That's what it means. But in the case of the conventional one, we assume equal weight for all the observation. No one is more informative than the other. But right here, some are more informative and some are less. Now, you know what we do in the conventional linear regression, right? We normally want to estimate the beta naught and the beta 1, okay, using an approach that can minimize the residual sum of square. I think you know that. We're also going to do the same thing here, except that we're going to be what? We're going to take into consideration the weight. Do you see WI, right? Okay, this is the residual sum of squared, okay, of the weighted least squared. Okay, so I want you to take note of that. Now, and look at what I said here. This is correspond to what I said the other time. I said, note that in this weighted sum of squared, the weight are inversely proportional to the corresponding variance. Of course, we expect that weight should be inversely more weight, right? Less variance. Okay, less weight. Okay, more variance. That's what it means. Okay, so take note of that. Now, what would be my beta naught? What would be my beta 1? My beta naught and beta 1, if you take a look at my beta 1, would be in terms of weight. Okay, so you can see the weight coming in. Okay, and let me tell you, if you look at the new beta naught, the new beta 1 that you obtain, putting it to, they will no longer, the beta naught, beta 1 here will no longer be called OLS estimate. that will be called WLS estimate. You know, the conventional one, where the constant variance hold, we basically call that ordinary least square estimate, right? But now we call this one weighted least square estimate. So if you want to go by algebra, they are still unbiased and their variance have been stabilized. Okay, you remember the other time I show you some formula, right? What is the variance of beta 1? What is the variance of beta naught? Right? Now, this is going to be the variance of beta naught, the variance of beta 1 when you are talking about weighted least square. The only difference between this and the one that we had before, there was no weight in the other one. But right now, you can see weight, right? Okay, so take note of that. Okay, and of course, we can go whatever we do in the other approach, we're also going to do that here. Now, what if I want to go from simple linear regression to multiple, where I got more than one variable? You know, the other time, what I just explained is when you have one explanatory variable. What if in a situation where you got more than one explanatory variable, and you basically want to obtain the weighted least, sum of square residual? Of course, you remember the other time where we use y minus x beta transpose. The only thing that you're actually going to come in is the W. The W here is a matrix. So which I wanted to take note. Okay, but let me tell you, when we're dealing with the ordinary least square, and we use a matrix approach, how do we find what is basically, you know what I'm trying to say is, if I have y equal x beta plus the error, okay, now if a situation where EI follow normal with a constant variance, you know, we normally use this guy. Do you remember that? You remember that? But what if in a situation where this guy is no longer homoscedastic, okay, but this guy is now that, then what I'm going to have is now going to be this. Take a look at that. Do you see that there's going to be a weight in, as part of, so if I want to write it the way, if this guy is the OLS, but the new one is WLS, I'm actually going to have, do you see that? Weight has to be in between. Look at that. Okay. Now I want to go back to the linear regression again. So going back to the linear regression, and if I consider the variance of the error, in terms of weight, I said sigma squared divided by what? W, right? I'm going to go back so that you'll be able to see. Okay, do you see that? Sigma squared divided by W, right? Okay, if I want to put the observation into consideration, I'm actually going to have this guy. The variance of error equal to xi squared sigma squared. What is the meaning? It means a particular observation has its own weight. That's why you see xi squared. Do you see that? Okay, now, if I want to go algebraically now, how do we transform using linear algebra? Now, if you take a look at this, well, what am I going to do if I want to get a constant variance? If I want to get a constant variance, it's more or less like, divided it by SI squared, right? If I divide it by SI squared, right? Now, if I have a constant, what was the S squared before? It was X. Do you remember in statistics, if I want to find the variance of 2x, if 2 is a constant, what happened? 2 squared, right? Variance of x, right? So it means this x squared before was just an x. So what I need to do, if I want to transform linear regression model, I would divide linear regression module by X, which means if I have two variables, X and Y, you know what I'm actually going to do? I will divide Y by X. Then the X that I'm actually going to use is going to be 1 over X, and my error is going to be the former error. Look at that. The EI was the error that was heteroscedastic. I will divide it by Xi. What am I doing to both sides? I'm dividing them by Xi. When I divided them by Xi, I got a new module. Now look at my new module. Yi star, okay, and the Si star. This is a transformed module. This is not the original module. The original module was actually this guy here. But what happened here? There was a violation. How do I know? The variance of error is what? Si squared sigma squared. Okay, and I want to transform the module. So what we're trying to do now is to divide the response variable by X and divide the error by X and use the reciprocal of the predictor. That's exactly what we're doing here. Take a look at that. In the end, if you now want to find, now I want to see now whether we have solved the problem. Let's see whether we have solved the problem now. So what is the new error? What is the new error that we got? It's old error divided by what? Old error divided by Xi, right? Now I want to find the variance now. The variance of the new error, which is going to be the variance of this guy divided by this guy. And this guy is a constant, right? Now, if this guy is a constant, I'm actually going to have, that would be squared, right? Then the variance of the error. Which error is this one? The old error. Let's go to the old error. What was the old error? I want to put that now. 1 over Si squared. What was the old error? The old error is Xi squared, the Si squared sigma squared. What happened now? What do you have? Constant variance. So this is to show that we've been able to transform that model, even without conducting any test. Mathematically speaking, the variance of the new error now will be sigma squared. And what has happened? What has happened is that we use a weighted model on a weighted relationship, then the variance will be constant variance. I told you the other time, agreement. There must be an agreement between the model and the reality. Okay, so which means the same thing if I now want to get the sum of square, of course, I'm actually going to put into consideration that, oh, my new Y, the Yi star is the old Y divided by X. And the new predictor I'm using now is 1 over Xi. So, and of course, the weighted residual sum of square, the weight now has that relationship, which means Wi equal 1 over Si squared. So take note of that. And what I was saying, hence the weighted least square solution is the same as the regular least square solution for the transform model. So which means the moment we have transformed the model, we are now back at what we were doing before, because we now fixed the violations. Okay, so I just want to, what I'm trying to show you here is how to fix the same problem when we're dealing with the multiple linear regression. In the multiple linear regression, the variance of the error will no longer be sigma square, right? It's going to be the inverse of the W multiplied by that. Don't forget, in the linear regression, what was it? In the linear regression, it was this guy, right? But in the multiple linear regression, it is basically W raised to the power minus 1 sigma squared. And of course, we've been able to tell the world that the moment we do all that, we're actually going to have a sigma squared. But you don't need to be worried about all that. I think I derive, that's before. This is more or less like, how do we go from transforming the model all the way to the weighted least squared estimate. But you know what I'm going to do next? I'm basically going to walk you through an example. I think I still have like 15 more minutes, right? Okay. Now, under the advantages in the transform module, the interpretation of the coefficients can be difficult. That is what I want you to see when you transform, because the variables are, even though you solve a problem, the variables are no longer original. Does that make sense? So you have to put that into consideration. That is for the transform. But if we're using the weighted least square, the advantage the weighted least square has is that the interpretation will still stay the same. That's for the weighted least square. But for the other one, I told you the other time that we have two ways, right, to face the problem. We could transform, or we could go by way of a weighted least square. Okay, so and let me just say this because I need to mention. I said in the transform module, there will often not be an intercept. When you transform using transformation, the intercept is going to go away. Okay, and which means if there's no intercept, then you cannot rely on your F test and the R squared, because the F test and the R squared actually depend on the intercept. Does that make sense? There are some people like they're going to say, in most of the time, intercept does not really make sense. Why do we need to include it in our model? We just have to. Look at this now. Because when you don't have intercept anymore, okay, then that will actually affect F test and the R squares. Okay. And another thing I want to say, the weighted least square gives us an easy way to remove one observation from a model by setting its weight equal to 0. And we can also downweight outlier or inflection point to reduce their impact on the overall model. So which means the weighted least squared is a robust method that can actually do well in the presence of violations. I'm going to walk you through an R. Let's say, how do we do this in R? We have a data set, which is on hours and score. Take a look at that. Hours and score. And we basically want to look at the effect of hours on score. Maybe hours study. The hours study by students on their score. Does that make sense? And we fitted a linear regression. Look at that. We fitted a linear regression. The response is a score. And the explanatory variable is the hours study. And in the end, what happened? Of course, we can see our model is actually giving us a very good story here, that the R square is going to be 62.9%. But there is something, before we can trust this model, we need to conduct a test on whether constant variance is violated or not. Okay, if a model is good, okay, the model may be sick. It's just like somebody who work very well, work excellently in a company, but that guy is sick. Of course, if that guy is sick and that sickness is stamina, that will eventually affect the person's performance, even if he is performing now. Now, we can't trust this result until we do something. And this is what we want to do. Test of heteroscedasticity. Because merely looking at your data, you may not know which one give more, whether one is more informative or one is less informative. You don't know. But we got a way to investigate that. Okay. The number one way of investigating that, you can look at the residual plots. Of course, you're actually going to see here you don't expect them to have a constant variance, but you can also go by way of conducting a standard statistical test of heteroscedasticity that we call a Brecht-Pagan test. if you want to test for Brespegan, you need to load it in your package, LM test. Then you're going to write BP test module. Where did I get module from? You see, module less than LM. Can you see that, right? Now, in the Brespegan test, the non-hypothesis of the test is that there's a constant variance. The alternative is that there's a violation. Okay. Now let us take a look at the p-value now. Oh my God, compared to 0.05, what happened? You're going to reject, right? You're basically going to reject. And when you reject, so this is what is it called? The alternative, the non and the alternative of the test. Now there's a violation of constant variance. Then what are we going to do? Then we need to conduct a weighted least square. There's so many ways to do a weighted least square, but look at what I want to do. WT less than minus 1 over LM. Why do I say 1 over? You know that reciprocal, right? I can do 1 over that. ABS is an absolute value, module, residuals, okay, or module fitted. Don't forget when we were, if you want to investigate the constant variance using the residual plot, it is you are plotting residual against the fitted. And you don't want to see a pattern, right? And of course, you expect, you know, at any values of the fitted value, the residual should be the same, right? Okay. So, and that's why we're actually using that code. Take a look at the code now. I'm going to say WLS module is going to be the score on hours. Our data is that, and the weight is WT. We have already defined WT. Then we're going to run the module again. Do you know the module we are running now is no longer an OLS? It's going to be called WLS. It is somebody is going to say, oh, this is an OLS after an intervention. Can you see that, right? And that's exactly what we have. And do you know, if you really want to know whether you solve the problem, you know what you're going to do? You can conduct a Brespegan test on this again. Does that make sense? You conduct a Brespegan test on this. What do you expect? The Brespegan test, you should be, you should not be able to, you shouldn't reject the non-hypothesis if that transformation has worked. What will now be the conclusion now? We are no longer going to be focusing on the other one. If you take a look at what I have now, the weighted, if you really want to know whether the two modules are actually, which one is more fantastic, can you go to the residual standard error of the OLS? The residual standard error of the OLS is 9.224. Do you see that? Now, what is the residual standard error of the WLS? 1.19. Oh my God. Do you see that of the WLS? Of course, that of the WLS is smaller. That's what we mean here. I said the weighted least square module has a residual standard error of 1.199 compared to 9.224 in the original simple linear regression module. If I basically want to know whether a module is better than another module, we can compare the residual standard error. And I said this indicates that the predicted values produced by the weighted least square module are much closer to the actual observations compared to the. Now, this will happen. Why are we using module? We basically want to explain. Is that we want to explain or we want to predict, right? But right now, we actually want our module to predict some values. You know, we already have exact we have values for Y that we're going to call actual values. Then we want our module for any corresponding, for any actual values of the response, we want our module to make a prediction for that. And let me tell you this, a module with a lower residual standard error, okay, whatever that module predicts will be very close to the actual value. That's exactly what we mean here. Now, we said the weighted least square module also has an R square of 0.6762 compared to 0.6296 in the original. Of course, if there's a marginal kind of difference. If you take a look at that, the R square will tell us how much the percentage variation in the response is being explained by the predator. And I said this indicates that the weighted least square module is able to explain more of the variance in exam score compared to the simple linear regression model. This is where we're going to stop today. Any question? Go ahead. Oh, if you want to estimate the mean. Oh, that's it. That's a very good question. Exactly, in a way. But if you want to compute the mean, right, you may not rely. If you really want to know the mean of the original mean of the data set, you use the former one. But except that the original mean will mislead in the sense that some observations have more information. Does that make sense? So if I really want to say this, if you still want to find the mean, still use the original, of course, because before we go into statistical inference, we do descriptive statistics where we report what happened, what we see. But when you go inferential, okay, you now need to look at the appropriate method to do inference. Okay, what is the essence of doing of what we're doing here? The essence of doing this, we really want to know the effects. We want to actually quantify the effects of a predator on the response. Okay, and the effects now we're able to get that after we've already fixed what happened. I mean, the problem in the model. But if you want to get the mean, you have to use the original one. Because the original one, you are reporting what you see in the data, whether there's a problem or not. Descriptive statistics should reveal that. And that is the reason why we don't go inferential without first looking at descriptive. Because in the descriptive you have done, you're actually going to sense a problem. And the descriptive will give you the sense of, oh, maybe there's a violation. Maybe I should try something this in my inferential procedure. That's a very good question. So use the original model to figure out the mean. Any other question? Now there's going to be, of course, your exam is on Friday. You know that, right? So I will advise that you actually we meet here. You're going to be here 5 minutes to the time. 5 minutes to the time, you already have your booklet and exactly the class time, then I will ask you to start. Does that make sense? Okay, so on the exam, of course, there's no any new stuff. It's just what we've done before. So focus more on what we did in the midterm one practice, and the assignment that you've done is basically going to be easy. Okay, so make sure you stay safe, everyone, and have a very beautiful day. Bye for now.